Well, of course, this is the 916th meeting of the Amateur Telescope Makers of Boston, founded in 1934, and we absorbed the Bond Astronomical Society back in the early 70s to make us one of the oldest and largest astronomy clubs in the country. Pretty active club as well. So welcome here tonight, you guys. Thanks for coming out on such a cold, windy night. I really appreciate it. So, you know, I like to move things along pretty fast, so why don't we just get started and see where this carries us. This part. For the Absorbing Committee report, Glenn, is Bruce here tonight? Let me see Bruce. Glenn couldn't make it tonight, so he asked me if I would do this for him, which of course you know I gladly would do it. So as far as upcoming sky events, anybody recognize this picture? Anybody know what that is?
It says it's a Prague.
It says it's in Prague. It's the astronomical clock in Prague. If you ever there, check it out. It is amazing, amazing. So I just wanted to add a little color to these up and coming slides. So I'm sure Glenn put this in. There's an eclipse of Algol on Thursday, January 17th. I expect that's the minimum brightness. Maybe it's, I don't know. I didn't ask him the details here. But apparently he wants to have a clubhouse event that he's going to begin at 5. So 7:49 might be the minimum of that. I'm sure he'll give you more information as time goes by. If you've ever watched Algol in eclipse, it's actually a fun thing to watch. It's relatively short, and so you can actually, over the course of a few hours, you can actually watch it go from, I like to watch it go from a minimum back up to the brightest again. And it's kind of cool. You can see it. It actually is pretty dramatic, all things considered. So that's a pretty good thing, and that happens every 2.4 days, I think. Something like that. So that might be something you might want to check out. Of course, the big event for January is the total lunar eclipse on Sunday, Monday night, January 20th to the 21st. That Sunday is the evening of Martin Luther King Jr. Day. So a lot of people have it off the next day. It's not a school night. That's a late eclipse. It doesn't get started until late in the evening. But it's total for us. We pretty much have center stage here. So I'm thinking about offering a member event at the clubhouse. I'll see if I can drum up enough interest in that. But you should definitely take a look at that. There won't be another one for 3 more years, visible here from New England. So do take advantage of this one. We'll keep our fingers crossed for the weather. Also, in the morning of January 22nd, there's a very close, beautiful conjunction of Venus and Jupiter. Get my little pen. A close conjunction of those guys in the early morning sky. I don't know if you have the opportunity to be up early enough, but Venus and Jupiter are converging now. I looked at them yesterday morning, and they were really quite pretty. They're low in the southeast at about 6 o'clock in the morning, and so they're really pretty to look at. So I encourage you to go out and watch that happen. And as I said, on the 22nd, they're going to be they're going to be really 2.5
Be careful, Venus and Jupiter are two different.
They're what?
One's female, one's male.
Oh, well, be careful with that. They are always
So be careful of your words.
Oh, all right. Oh, okay. I see. Yes. There they are. Perfect. All right, well, let's move on then. On January 31st, there's a really close pair up of the Moon and Venus. That circle right here, this is Sky Safari 6 Pro, that circle's 3.5 degrees. So that's the field of many finder scopes. So you can see, it gives you some idea of how close the two objects are going to be in the sky. And if it looks like there's going to be an occultation later that day, there actually is not. The moon passes, at least for us anyway, the moon passes a little bit to the south of Venus, and so we won't see any kind of a possible occultation. Lastly, Glenn put for Wednesday, February 13th, in the early evening, Mars and Uranus will be in close proximity. And again, that's a 3.5 degree aperture ring there, meaning that you'd be able to see both of those in a finder scope or certainly in a pair of binoculars. Was it last month that Mars passed particularly close to Neptune? And we were up at the clubhouse and got a look at that. This is another close conjunction here. So that's pretty good. So those are the up-and-coming sky events. Dick?
When the moon passes Venus, do you know how close they're going to be?
At its closest, they pass about 0.5 degree apart.
So it's like the size of the moon.
About the
So
distance
it'd be
between
a
the
guide for finding Venus in the day. Right?
Oh, that's a good point. You know, if you've ever wanted to find Venus during the daytime, that is a pretty fat crescent moon right there. Find that first, and then it should be very easy to find Venus. I was out looking at, like I said, the other morning, maybe on today, Thursday, probably Tuesday morning. I had a binocular sighting of Venus at about 8:30 in the morning. And then taking the binoculars away, I could easily see it in the sky with my naked eye. So it's fairly bright. It's near greatest elongation west now. So it's in it's pretty easy to see. You should check it out. A lot of people are surprised to find out that you can see Venus in the daytime. But at -4th magnitude, it's actually a fairly easy object to look at in the daytime. And it helps to have some target to help you out. So yeah, definitely check it out. I like to observe Venus in the daytime with a telescope, just because, you know, it's nice and high in the sky. And I know the air in the daytime is somewhat unstable, but I like to do it. Anyway, the LVAS Observer's Challenge for January, as Glenn would have told us, is NGC 1514. And I mentioned this last month. It's a planetary nebula here, down here, near, well, let's see, here's Perseus here. This is Algol here. So here are the Pleiades. So this pair of stars is pretty easy to find. And it's a pretty easy star hop to get to this planetary. It is a 9.4 magnitude central star. I don't know of any other planetary in the sky that has a 9.4 magnitude central star. I could see the central star in my finder scope. I have an 80mm finder on the big telescope, but I could see it. And at first I thought, what is that star doing there? Because on the charts, there's no star there. Turns out it's the central star to the planetary. And I found that with aperture, that object really comes alive if you employ an Oxy-3 filter. If you don't have enough aperture to drive light through an Oxy-3 filter, try a UHC filter or a sky glow, and you'll see the nebulosity pretty easily. It's a really pretty planetary. I'd never seen it before until it came up in the LVAS, and I'm really glad it did, because I would have never thought to look at it. But definitely check it out. It's an amazing object. And Roger's already starting to look at 2175, I think, in Orion. And he was talking to me tonight as I was driving here, saying that he spent 2 hours sketching that the other night. And he said it's an amazing nebulosity in Orion. So something to look forward to. I know Mario's not here tonight, so I can share with you my new campaign to make lunar observing great again. I'm going to have hats made. Hats. But I'm going to try and get more people to buy into looking at the moon. If you think about it, it was probably the very first object you ever looked at, right? Right? Yeah. So come on, I looked at it tonight. It's really cool. It's got craters and stuff. You should see it.
You've seen one crater, you've seen them all.
Well, I know that's so. You know, every morning I know I'm retired now, so I have the luxury of sitting around just surfing the internet while I sip my coffee. One of the websites I look at every day is the Lunar Photo of the Day, and the website they're almost like reruns. Somebody took over the website, and they're posting things back from 2009. But what I especially like to look at the pictures and when I read the captions is that little by little I'm trying to learn some lunar geology, because that's what the explanations oftentimes are. And so I like to go back up and look at the moon, because now to me all craters aren't exactly the same. And sometimes there are challenge objects, and sometimes it's just a lot of fun. I know Mario likes the deep sky. A lot of folks like deep sky, and some people like double stars, and some people like variable stars. I kind of like all of that stuff. And when the moon's in the sky and I can't look at deep sky objects, guess what I look at? The moon. If the sun is up, then I look at Venus, or maybe I'll find Jupiter in the daytime, or sunspots. Not that there are any these days, but I try to do astronomy whenever it is offered to me. And so please don't give up on the moon. It's a really cool object. You should really try it. It might bring back memories. Even in the smallest of telescopes, I've become enamored with small refractors. And so looking at the moon through 60mm refractors or 75mm refractors, the views are amazing. They really, really are. Some of these vintage refractors have tack-sharp optics, and they're just amazing to look through. And they're not suited for, you're not going to look at the nebulosity around NGC 1514 with a 2.4-inch refractor, but gosh, the moon and the planets and double stars are amazing. So no matter what telescope you have, I would encourage you to get out and use it, to dust it off and get it outside and just look at the moon. It's going to be in the evening sky all week. It's going to be awesome, you guys. So I think you should do that. Anyway, that's enough of that. Anyway. All right, so it's time for our guest speaker for the evening. She is Kelly Blumenthal. Her talk is Galaxies from Observations to Simulations. And I'm going to read her bio. I'll let her get set up with her computer. So I'm going to unplug my little guy. let her plug in her little toy. And I'll come over here. While you do that, we'll do this. It should work, right? It worked before, right? These last words, right? So Kelly Blumenthal is a 50-year PhD student who is currently a visiting scholar at the Harvard-Smithsonian Center for Astrophysics and a National Science Foundation Graduate Research Fellow. She earned her undergraduate degree in astronomy and physics with a minor in saxophone performance. Awesome. From Boston University. In 2016, Kelly received her master's degree in astronomy from the University of Hawai'i and moved back to Cambridge, Massachusetts to finish her doctorate. In addition to her research work, Kelly has been heavily involved in outreach programs in Hawaii and just published an educational book for high school students, Cosmic Inflation Explained.
So I smash galaxies together in a computer for a living. That is what I tell everyone, and that is the sentence I will say for the rest of my life. So I look at the interactions of two galaxies. Can you hear me? Is this okay?
Yep.
Oh, thank you. I look at the interaction of galaxies in simulations, so in computers, not looking out into the night sky at a beautiful, beautiful image like this. I pay absolutely no attention to what's actually going on in the real universe except to try and understand the physical processes that are going on. But that's not at all what I'm going to be talking to you guys about today. Today I'm going to be talking about how our perspective of the galaxy itself and galaxies in general has changed throughout history. And to do that, I'll start with this guy, the most obvious galaxy in our night sky, and that's our own, the Milky Way. So the name itself comes from the Latin Via Lactea, which means literally the road of milk, and that's really because it looks like spilt milk in the dark night sky. Now there were three Greek natural philosophers who kind of argued and had very strong opinions about the nature of the Milky Way. Democritus and Anaxagoras thought that it was a very distant object that was made up of many stars. But about 100 years later, Aristotle talked about the same topic, about the Milky Way, about the Via Lactea, and he disagreed vehemently. He thought for certain that the Milky Way was the byproduct of the intersection between the terrestrial sphere, where all of man and humanity lived, and the celestial sphere, where everything else was, where the gods were. And that there was, at this intersection of these two spheres, there was an ignition of gas that ignited the Earth's upper atmosphere and formed what we consider to be the Milky Way. And unfortunately for physics and astronomy, Aristotle's views of cosmology really were widely accepted for centuries after he lived. And it wasn't really until about 400 years later, Aristotle, that astronomers started to question many of his assumptions that he'd made about the Milky Way. One Arabian astronomer, in particular Alhazen, this guy right here, realized that if the Milky Way were actually in the Earth's atmosphere, there would be, or if it were very nearby, then it should exhibit a parallax. And you can think of parallax in a very simple way. So if you stick your arm out in front of you, and you give me a thumbs up, and then you close one eye and you open the other eye, and you close one eye and you open the other eye, you'll see your thumb kind of appear to move back and forth. And that back and forth motion is what we call parallax. And stars' parallax work in a very similar way. So the Earth moves around the sun, and from one position 6 months later to another position, you have two viewpoints that are basically like your two eyes. And the Earth looking at a star that's relatively nearby at one period in time will appear to see the star in one location in the sky, and 6 months later it'll appear to be in a different location in the sky. And the angle subtended by those two images would be its apparent motion or its parallax. But if the star is actually farther away, so if we move this star farther out, the apparent motion in the night sky is much smaller. And so the parallax is thus very small. So if something is very far away, so perhaps if something is, let's say, 8.5 kiloparsecs away, then it'll have no apparent motion in the night sky. And that's exactly what Alhazen found, that the Milky Way has no exhibited parallax. And he concluded very much rightly that this object, whatever it's made out of, is not the inside of the Earth's atmosphere, but is actually very far, far away. As to what it's made of, That wasn't a solved mystery until Galileo invented the first telescope in the 1600s. And he used this invention to observe the Milky Way. These are some of his first observational drawings of the Milky Way. And he determined that the Milky Way is actually made up of individual stars. And it wasn't just a homogeneous group of stars. It was individual stars that seemed to be very dynamic, very clumpy. Of course, very much to the Catholic Church's chagrin at the time. Now, Thomas Wright came a little bit later. He was the first to correctly discuss the shape of the galaxy in his treatise, A New Hypothesis of the Universe. And in it, he wrote that its appearance, the Milky Way's appearance, was an optical effect due to our immersion in what locally approximates to a flat disk of stars. And that really established our idea of galaxies like our own, spiral galaxies or disky galaxies, as more or less a flat disk of stars. Now, the philosopher Immanuel Kant actually, who is, I would consider best known for his works on reason and perception, actually dabbled in astronomy in his early years. And he expanded on Wright's work and noted that there must be other objects that are very similar to the Milky Way that are very far beyond it. And he dubbed those island universes. Now, the actual first recorded observations of galaxies outside of our own dates back to the mid-900s. The Book of Fixed Stars by Arab astronomer Azofi contains the first observations of the Andromeda galaxy, which he termed a little cloud, and the Large Magellanic Cloud. Now, of course, despite their name, Europeans and Magellan didn't know about the Magellanic Clouds until Magellan made his voyage in the 1600s. But even centuries after, people kept on observing objects in the night sky that appeared kind of nebulous and spiral in shape. And so aptly, they were called spiral nebulae. And they were really the subject of much debate in the astronomy community. Now, if we fast forward to 1920, at this point, astronomers have been arguing and debating about the nature of spiral nebulae for centuries. And they schedule a formal debate to determine their true nature. The so-called Great Debate featured two astronomers. We have Shapley over here and Curtis over here. Shapley believed that the spiral nebulae were absolutely clouds of gas inside our own galaxy, and that our galaxy, the Milky Way, was the only one in the universe. Curtis, on the other hand, believed that the Milky Way was one of many galaxies, and these spiral nebulae were actually what Kant would have called island universes outside of our own galaxy. Now, one of the most compelling arguments in support of Curtis's position was based on measurements of the distance to Cepheid variable stars in Andromeda galaxy, which I just you learned about last time. But for those of you who weren't there, the Cepheid variable stars were discovered by Harvard's own Henrietta Swan Leavitt in the early 1900s. And she noted that certain stars have a very predictable periodicity to brightness, a very stable periodicity to their brightness. That scales very reasonably with luminosity. So if you have a lower luminosity star, more red star, then it's going to have a much faster period, and it'll change its brightness much faster, or a much faster time scale than would a much higher luminosity star. So if you can measure the periodicity of the star, if you know this already, then you know what its luminosity should be, and from that you can actually determine the distance to that star. And these are these so-called standard candles that we're all really looking for. So better observational data of Andromeda's Cepheid variable stars from Edwin Hubble confirmed that Curtis was actually 100% correct. And with that, our concept of the universe expanded significantly. And this has really been, moving forward, this has really been facilitated by our ability to measure distances to objects in really indirect ways. And by that I mean we're not taking a ruler and we're not counting how many feet there are to the moon. We're using what astronomers use is called the distance ladder. And these first two we've actually talked about already, of course, the parallax and Cepheid variables. I will say that there's many more rungs to this ladder than I have here. This is a very simplified version of this ladder. But just to go through a couple of the key points that I think are really interesting. The Tully-Fisher relationship, for example, relates the mass of a galaxy, which is intrinsically related to the rotational velocity of that galaxy, with its luminosity. And just as we used the luminosity of Cepheid variables to determine the distances to those objects, we can find distances using the Tully-Fisher relationship. Type 1a supernovae, of course, as you all probably already know, are the resultant explosions of a binary star system in which one of the stars is a white dwarf, and it is accreting matter onto its surface. As it reaches a certain mass point, there's a really violent explosion, and that violent explosion is what we know of as a type 1a supernova. And that supernova actually has a really predictable and well understood brightness curve, or brightness as a function of time. It's a light curve. And they're all really remarkably uniform. That's what makes type 1a supernovae so unique, is that supernovae of the same peak brightness are at the same distance. So if you know the distance to one supernova from another distance indicator, say it's in the same galaxy as a Cepheid variable, then you can figure out the distance to progressive supernovae, and you can build out your ladder that way. As we're going out in the ladder, Hubble, the same Hubble as before, of course, started measuring the distances to nearby galaxies as well as their velocities, and found something pretty remarkable, that there seems to be a kind of flow in the universe, at least in the local universe, that galaxies' distances actually scale with their recessional velocity. And though this isn't true everywhere in the universe, the constant of proportionality, this Hubble's constant, is something that's a fundamental parameter in all of our cosmology models today, and something that's actually still pretty hotly contested. But perhaps one of the most fundamental rungs of this distance ladder is redshift. And redshift is a measure of an element's emission or absorption line from the known quantity measured in the lab on Earth. So if we measure the spectrum of a galaxy, or really any object we see in the universe, and we see emission or absorption features, we can use the spectral features of that object to figure out its distance. But just to dive a little bit more into what I've just said, of course, light itself is organized on the electromagnetic spectrum, from really low energy radio waves to super high energy gamma rays. And of course, our perception of color comes from the visible spectrum, which is a tiny fraction of the entire electromagnetic spectrum. But another kind of radiation that astronomers really care about, it's really not another kind, it's just a different way of looking at it, is atomic emission or absorption. And so this occurs when electrons in thin gases jump between energy levels, which you can kind of see here. And of course, I will say that this is not an exact representation of what's actually going on, but it's a very good way to illustrate it. And actually, if you calculate the energy based on orbitals, it turns out to be perfectly fine. You don't need to go into quantum mechanics to really figure that stuff out. But if there's any physicists in here, I apologize. So the process looks something like this. You have a happy little electron going around a proton in its orbital in its energy level, and a photon comes in. And that photon, if it has the exact right amount of energy to bump it up a level, or 2 levels, or 3 levels, then it will do so. So it'll jump to a higher energy level that is associated with the photon that it just absorbed. And so if you're looking at it that way, then you would see a dark spot in your emission spectrum. But the electron will eventually fall back down, and it will release this photon of the same energy as the difference in its energy levels. And so in that case, you would see an emission spectrum. So each element, hydrogen, helium, lithium, beryllium, every element that we know of has its own individual spectrum, its own set of lines that look kind of like a barcode. You can really think of it as like a spectral fingerprint. Just like each individual person has their own fingerprint that's unique to them, each element also has a unique spectral fingerprint. And we can use these to figure out not only what the universe is made out of, but also we use these lines to figure out how far away objects are in the universe. Sorry, that didn't work as well as I thought. So these are the very spectral features that I was talking about to determine the distances to objects that are significantly far away. So getting back to our narrative. once we came to terms with the fact that our universe is not comprised of a single galaxy, our own single galaxy, our concept of the cosmos changed significantly. Not even a century after the Great Debate, actually probably about 70 years after the Great Debate, we launched the Hubble Space Telescope into orbit around the Earth. And with it, we have gotten an incredible amount. So in this image, which is the Hubble Deep Field, which I'm sure you've all seen, there are 6 stars. I'm pretty sure there's 6. There's 1, 2, 3, 4, 5, and 6, maybe up there. Everything else in this image is a galaxy. This is clearly not Hubble's only claim to fame, but it's really serves to put our galaxy into perspective. If you're looking into this image and you're seeing so many diverse objects that are all galaxies like our own, you have to figure that the universe is about as diverse and as plentiful as life is here on Earth. And one key aspect of this diversity are objects such as these. These are merging galaxies. These are the galaxies which are nearest and dearest to my heart and the hearts of my advisors. They were originally just called peculiar objects. If you've ever heard of ARP's archive of peculiar objects, this is what he was looking at. Mergers have actually proven to be one of the most fundamental evolutionary pathways for galaxies. Our understanding of galaxy formation and evolution is based almost entirely on galaxy mergers, which is why they're really so important to study and why I will continue to ask the government to be paid to study them. But dwarf galaxy mergers are perhaps even more fundamental. Now, when astronomers say dwarf, we really just mean something that has a very low mass. But they really have some unique properties that make them very different from massive galaxies. And one of the most crucial elements of modern cosmology is that small objects, like dwarf galaxies, come together to form larger objects. And again, smaller objects come together to form larger ones, and eventually larger ones. And this process is called hierarchical structure formation. And if you think about it, this process is actually kind of hard to prove observationally. Hierarchical structure formation is a dynamical process, which is not what we see when we look out into the universe. When we observe something in the universe, we observe a snapshot. If we try to put things together, it's like trying to piece together different scenes from different movies to try and get a uniform plot that makes sense. It's not necessarily what we're going to be able to get, but we can make a pretty good inference that what we're looking at is roughly self-consistent. Now, the most massive structures in the universe are clusters of galaxies, very much like this. Often these act as giant cosmic telescopes, bending the light of background objects as their light is coming from the early universe on their way to us. Their light can get bent into arcs and distorted images of galaxies like the ones we see here. Images of Einstein rings and Einstein crosses, I'm sure you've all seen before. But this is all basically due to the fact that a giant cluster of galaxies has an immense dark matter halo. And that halo is so huge that it can sufficiently bend the fabric of space-time that we can see these huge, like, arc minutes across images of distorted galaxies, which is definitely not something we can do with just individual galaxies. Although that's not to say that gravitational lensing by individual galaxies is not a thing, but for a later time. Just to say also that these environments, as you can probably tell, are incredibly rich. And the evolutionary mechanisms by which individual galaxies within this cluster evolve is extremely different from galaxies that are evolving by themselves in the field or in small groups or in mergers. Now, beyond massive clusters of galaxies, we actually have the cosmic web. And you can see here and here indications of clusters of galaxies that have formed. Oh, and it's done. Oh, no, okay. Now, more than anything, this shows us that there's an indelible link between the structures that we see today and the structures that came before it. And that's really a fundamental thing when it comes to thinking about cosmology in kind of an abstract way. So with the advent of computers, we were able to start simulating galaxies. And the earliest way that we were able to do this were integrations of test particles within a single potential. So these test particles have no mass. It was, I think, in the 70s, the early 70s, when the first simulations of at least merging galaxies came to light. They were test particles sitting within a spherical potential, and you could isolate which part of the spherical potential you wanted to look at, so you could simulate a flat disk of stars without actually having to think about what the potential of a disk looked like. Now, these were, of course, very limited, but the techniques that we learned from these exercises proved really valuable for computational astrophysics that came after. So the next step was to develop n-body simulations, which approximate spherical, like solid bodies, more or less, as a collection of individual particles that do have a mass and do have their own gravitational potential. This is of particular use when you're simulating an object whose pieces you wouldn't expect to necessarily collide with one another, just like stars. So as you start increasing the number of particles you want to look at, the computational price gets significantly higher. So trees were developed to alleviate some of this issue. And much like an actual tree, a computational tree has leaves and branches that kind of sort the particles into a hierarchy of particles that the computer can then look at in an efficient way. And the computer will then solve the equations of motion and whatever else equations you're interested in based on these groupings, these hierarchical groupings, rather than individual particles, which speeds things up fairly significantly. So if you want to add gas to your simulations, that was all talking about stars. If you want to add gas to your simulations, one of the most commonly used methods is called smooth particle hydrodynamics, which is often called just SPH. So instead of treating, much like a tree, instead of treating each individual particle as its own separate thing, you treat particles as groups of particles as kernels, which are defined, the size of the kernels are defined by the particle density within the simulation. And the smaller the kernel size, the higher the particle density. And when you put this all together, you get something like this. This is one of my simulations. Just a single galaxy gets bombarded by another galaxy. You see these tidal features that form, clumps form, and eventually make their way into the center. It'll kind of equilibrate for a tiny while, while the other galaxy is somewhere over here, probably making its way back there. So the two galaxies can eventually merge and coalesce to form a single massive galaxy. So as the physics involved in the simulations got more complicated, really as we understood the physics better and we needed a better way to simulate these things, there was a need for new techniques that didn't affect the outcomes quite as much. So for treatments of gas, many modern simulations use something called adaptive mesh refinement, which instead of kernels that I showed before, defines this, it looks like a tessellated grid, and all of the properties of each individual grid cell are defined by the average gas properties within that grid cell. Now, of course, the ultimate goal is to build your own universe in a computer. Build your own universe in a computer is what you want to do. And if you have all of the computational components put together, the rest should be pretty simple, right? All you got to do is just add physics. The problem with that, of course, is that it's not quite so simple. The physics that goes into these large-scale simulations is incredibly complicated. And we don't have the kind of resolution or the resources to really understand most of what's going into it. Other things like the true nature of dark matter or the role of binary stars on evolution have, for the most part, eluded our observational abilities, but we have some pretty good ideas of what should be going on in these systems. And that's exactly what we've done. So in these two simulations, these are two different ones. This is Illustris Original, and this is Illustris TNG. And they're initially exactly the same. They have the exact same initial conditions. But what you'll see as this evolves over time is that the physics that goes into both of these is different enough to produce a significantly different outcome. And when I say different enough, I really only mean that there's a couple prescriptions that they changed from this iteration to this iteration. And some of the assumptions that they made here, they realized were wildly incorrect, even though they thought at the time that they were actually pretty okay. So you can already start to see how things are pretty dramatically different. And what this really just goes to show is you might think you're getting the physics right. And also, if you're reading a popular science article about some simulation that claims to have all of the physics right and do everything absolutely correctly, chances are they probably aren't. They just think they are. And there's a lot of things about the universe that we just don't understand yet. And a lot of things that we're trying to understand, we think we have a pretty good grasp on. But with stuff that's going to be coming up in the next couple decades, will probably change the face of cosmology as we know it. So you can see even when two simulations start off with the exact same initial conditions, just a tiny tweak in the physics changes it by quite a bit. So what's next in the world of galaxy research? At this point, our understanding of physics and our ability to perform massive simulations, really our computing resources has kind of reached a peak. So until computers get a lot more complicated, so like quantum computing, until we figure that out, there's not a whole lot more like super breakthrough science that we can do other than kind of iterating on what we've already done with illustrious TNG. But we're working our way to really understanding some of the physics ingredients that I mentioned before. And our computing resources are actually good enough that we can do small-scale simulations with really high resolution to actually understand the physical processes that are going on within these large-scale cosmological simulations. So I think that the future of galaxy research will really lie in improving our understanding of dwarf galaxies. Not only because they're so small that we can actually perform pretty high resolution simulations of those individual galaxies and then even their mergers, but also because they're the fundamental building blocks of hierarchical structure formation. They are the basis off of which our universe is built, and we don't really understand how they evolve individually and by individually I mean we don't understand how they evolve separate from a massive galaxy that might be nearby. And then, of course, eventually, hopefully, maybe sometime in the next 10, 20 years, JWST will be launched. It'll be really exciting when it is, but I'm not putting money on it. But that'll be the next generation of right-to-space telescopes. And it's likely to give us many more breakthroughs than Hubble has. Hubble. JWST will be particularly good at looking at the early universe because it's built to observe in very red wavelengths. So just like an object moving away from us, its wavelengths will be shifted toward the red. Objects that are very far away from us are also shifted very far to the red. But because of our atmosphere, it's kind of only possible to observe very early universe objects from space. So JWST will really give us pretty much the only opportunity to look at the very early universe. And it'll give us a very unique view of these objects and allow us to test all of our theories of galaxy formation and evolution, and really just cosmology in general. And so with that, I'll bring us back to where I started and ask for any questions.
Kelly, I have a question. Could we go back to the slide with the simulations, the two simulations?
Absolutely.
This is a really naive question.
I love naive questions.
So we'll pick on the right simulation since it's the more modern one. Are we looking at, does that depict densities of galaxies? Are those a gajillion galaxies all stitched together in the macro structure of the universe? Is that what it is?
More or less, yeah. So what the color that you're seeing here and also on the other side is the temperature of the gas. So what you're actually looking at is gas distribution throughout the entire box that they've used. And this box is 100 megaparsecs on side.
100 megaparsecs.
Yeah.
Now does that gas, so that's not exactly galaxies, that's just the distribution of gas.
Right. It's not necessarily just galaxies, but it does link galaxies together.
Mhm.
And for the most part, where you see these like big knots, those are galaxies
Okay.
or galaxy clusters.
Mhm. Nice. So that's to help us to understand the whole macro structure of the universe.
Yeah.
Okay. That's impressive.
I've read recently that they've been finding around our galaxy a lot more, I don't know whether you call them dwarf galaxies or
Ultra faint dwarfs.
ultra faint
Yeah.
dwarfs. Is that causing any re-evaluation of galaxy formation? Or I guess they said that they think that maybe another galaxy has already brushed us and is being gobbled up by the Milky Way.
Yeah, that wouldn't surprise me at all, actually. So ultra faint dwarfs are really exciting because we would expect to see them based on our cosmological theories, and the fact that we are seeing them now is very encouraging. So I don't think they're really changing anything so much. It's just like everybody's breathing a sigh of relief.
When I look at your pictures, I look at the sky and I look at pictures of the stars, the one thing that strikes me that's different about those than everything else that we deal with in the universe is that we have a scattering. Almost everything else in the universe tends to want to compress into something. And yet the universe itself is mostly empty, but then these very highly dense bodies, we call them stars or whatever we want. And we can talk about the stars or galaxies, whatever you want to do. But they are discrete points or discrete masses of things. We don't see that anyplace else in the entire world. And I don't want to say universe because then we get into that. But the one thing, the first thing that stands up from a scientific standpoint is the stars and the things are different from anything else we see. Why? I don't have the answer.
So I think really the only answer that could make any kind of sense is that stars and galaxies exist in a set of conditions that is significantly different by unfathomable orders of magnitude than anything we know on Earth. So we've been trying to recreate the kind of like plasma, like ionized gas conditions of stellar atmospheres. And we just can't get down to low enough densities to do that. We don't have the technology to be able to understand even the density of gas around the sun, let alone the nature of gas in other stars, much larger than the sun or much smaller than the sun. So
Well,
they're just very, very different.
Well, you always work and astronomers work on an n-body problem. But when you get very many of them, you can't do anything computationally with them. And so everybody finally goes and talks about it as a fluid, which is sort of an infinite body problem. And I'm looking at these things, this has to be a fluid thing of some kind. And I'm trying to see something in it that I recognize from any other fluid I've ever seen in my long years of looking at things. And
Looking at things
the
on
thing
Earth.
that still stands out is that it doesn't seem to want to come together. Now, if that has to do with the initial explosion or something, I don't know. But it's different, and it's the only thing in the universe that's that different.
You had some really detailed, like, spectral lines. Do you know what equipment provided us those fingerprints? Like, you remember seeing spectral lines displayed on, the classroom wall. It seemed a lot more discrete in your slide. They looked very precise to my eye.
It's probably just some spectrometer that a person on the internet had
Well,
lying around. It wasn't like a special instrument for astronomers only. Because they were, so those,
yeah, it's like a really, yeah, that one. Yeah, a little further.
That
See, they seem
this is
quite
all from a lab
distinct.
on Earth.
They definitely look like fingerprints in that side.
Yeah.
That's what you get from mass spectrometers and stuff like that.
No, it's just a.
Yeah, no, I guess I mean, the only thing I would say is maybe in your high school chemistry class, you didn't have good enough materials to actually look at the correct thing.
No,
We
exactly.
used to have students look at hydrogen and helium crypt tubes just with handheld spectroscopes, and you can see the spectral lines.
Yeah, you can see
Very
them really
clearly.
discreet.
They're very pretty, and they are barcodes. Every element does have a unique set based on the orbital, the electron orbits. And you're right, the Bohr model is relatively simplistic, but it does a nice job of explaining what these lines are. And yeah, you can see them. You could build a simple spectrum. You did grading spectrum, a little transmission grading, and hold it up to some of the newer squiggly bulbs. And you can actually look at the individual images of the bulbs when you break them into the spectrum. Because they're not a continuum, they're discrete colors that the bulb is pumping out. It's kind of
Actually,
neat.
if you have any CDs lying around, you can break up one of the CDs and stick, if you're interested in it, you can make like a serial box spectrometer, and you can look into the thing, and using the CD as your diffraction grading, you can actually see the spectral lines of whatever object the light is coming in from. So it's a very simple way if you have old things lying around. To do that.
Does the distribution and the proportion of dark matter vary according to the type of galaxy, or is it more or less the same different types?
Oh, what a great question. I was just talking about this earlier with someone. Dwarf galaxies have a very different dark matter profile than more massive galaxies. So that's one thing. Their dark matter profiles are kind of concentrated in a different way. So whereas you might have like a really steep peak at the center of a massive galaxy dark matter profile, it'll be more kind of cuspy and shallow near the inner part of the dark matter profile for a dwarf galaxy. So that's one thing. For the most part, we think that galaxies on average have what's called an NFW halo, which can be approximated as a spherical NFW halo, but that's almost certainly not true. Dark matter halos can be pretty triaxial when you actually look at them in simulations. So if we think we know what dark matter halos should look like, then we can probably figure out what galaxies should look like is the idea from that. But it does vary somewhat based on mass, and it does vary maybe not their structure, but the way that the galaxy is oriented with respect to the dark matter halo varies a bit based on the type of galaxy. So spiral galaxies sit within their dark matter halos in a different way than spherical galaxies do, and that probably has to do with the whole galaxy merging process and how their material all gets kind of swirled up and mixed up and kind of randomized as you create more massive structures.
Is it possible to create a visual representation of what the halos look like? Dark matter halos?
Oh yeah, most people don't listen to them because they're hard. If it's not a sphere, it's super hard to put into a computer to like do like an idealized like a small scale simulation. Yeah, no, I mean astronomers know that dark matter halos aren't spheres. We just ignore it.
Yeah, you said you're working on something different. What are you working on?
So one of the simulations that I showed you, the first dinky one, was the stuff that I had done for like my master's project. So that was looking at inflow of gas during mergers when you alleviate some of the assumptions that we make when we make these idealized simulations. But the stuff that I'm doing right now is actually looking at galaxy interactions within illustrious TNG and trying to gain some understanding of what the merging process would look like in a universe like illustrious TNG, and what assumptions we're making when we create these catalogs of merging galaxies. And say we can define some merger rate to be, this number of galaxies per redshift bin, or something like that. What biases are inherent in that, and how does that affect the theoretical simulations that we actually perform going forward from those assumptions.
So you'd mentioned your illustrious TNG. Is that a particular simulation? Is that something, like I've never heard of that before. Could you maybe tell us a little bit more about that?
Yeah, so the two simulations that I showed, with the one video that had the two simulations on it, one of them was illustrious, and this one on the right was illustrious TNG. And so they are cosmological simulations, really huge, large-scale simulations. Took
origin of the universe and its evolution over time.
Yeah. It took about, say about a year and a half, maybe each, of computing time on these supercomputers in Germany to run. And it's a collaboration that's run primarily through the Max Planck Institutes out in Germany, but also many people here and throughout the country, but mostly Lars Hardenquist here, who's my advisor at Harvard, is one of the main guys behind it. Yeah, exactly what you said. They're just trying to understand the formation of structure in the universe and everything that goes along with that. So
And
they're
it
trying to
lines
understand
up-
everything.
It lines up pretty well with what we see today. Like you've run it backwards and forwards. It just sounds so extraordinary. The computing power,
It is pretty remarkable, yeah. And for the most part, honestly, the illustrious TNG does a really great job of recreating galaxies that look very much like our own. But there are things that people are looking into that are not necessarily consistent with the real universe. So there's still definitely room for improvement.
Another question, do we have any examples of, you deal with merging of galaxies, and Andromeda is supposed to merge with us in a few billion years, but if we're in a local cluster and each one of those galaxies is coming together, or they're all being are there examples in the universe of super galaxies much bigger than Andromeda or Milky Way? Are elliptical galaxies, for instance, which is what I've read that they say Andromeda and Milky Way are going to become, are they the largest galactic objects out there, other than the superclusters, obviously?
Yeah, well, so the galaxies that sit at the center of massive clusters of galaxies are the largest galaxies that exist. But there are objects that are quite large. I think Mercurian something. I don't remember the name of it, but there is one particular galaxy that is, it's very rare. It's the only one that we know of its kind, that is remarkably large
Is
for
it
being so
spiral?
isolated.
Is it spiral, or is it?
I believe it has kind of like a disturbed morphology, more or less. So it kind of indicates that it recently underwent a very violent merger and coalescence. So like the final stages of merger, if it's not already completely merged at this point. Yeah.
So when the galaxies merge, if you have black holes at the center of each galaxy, then what happens then when, I assume they also meet? What happens at that point?
Good question. They merge? We don't know. So that's some of the things that people are trying to do with like gravitational wave studies, for example, is try to understand what happens when two massive objects like two supermassive black holes actually merge. And you would expect to see some kind of signature from that, but we haven't seen exactly that yet.
We have one galaxy that I know of that we've looked at over the years. It's two merging galaxies, which is called the Antenna and Corpus, NGC 4038, 4039. I don't know how massive they are, but I know that on the dark side you can actually see the two. They do look like they're interacting.
Yeah, they're so
It's very distinct that they collided.
my advisor in Hawaii is particularly obsessed with the mice, or sorry, with the antennae, and also the mice. But I didn't actually realize you could see. Can you actually see the tails if you look at it in the night sky?
Well, in the dark sky, not around here.
Okay, well,
Texas, yeah.
that's pretty remarkable. I didn't realize that.
Yeah.
All right. Well, let me see if I can get the lights to come back up. Didn't Glenn always have trouble with this?
You can do that.
I'm gonna try.
Oh wow.
That was not subtle, but there we go. Well, Kelly, thank you so much for your talk. It was awesome. We don't learn new things when folks like you come up and talk to us. So if there is nothing else to discuss, I think I'll call the 916th meeting of the Amateur Telescope Neighbors of Boston closed. And I'll bang my little gavel. You're right. Thank John Harrington for refreshments and have a safe trip home. Happy New Year, everybody. And we'll see you at the clubhouse and we'll see you next month. Thank you so much.